Rectifiers and filters. So far we talked about AC circuits. Now if you want to convert AC to DC, the AC-DC conversion process is called rectification. And here is a half-wave rectifier circuit. So where we have the AC voltage appearing on this side, on the secondary, causes a current to flow in the circuit in the positive cycle due to this diode, but the diode blocks the negative current. So with no capacitor in the circuit, what this diode and the resistor will do is it will only have a current in the positive cycle of the voltage appearing on the resistor, and for the negative cycle we don't have any current flow. Of course, this is assuming that this is an ideal diode. And with the capacitor in place, when the positive current flows, the current is going to increase, and then when we have the current start decreasing, basically the charging process on the capacitor will complete, so we will have the capacitor starting to discharge in the resistor, so through the resistor. So for the positive cycle, when the current is increasing, the capacitor is going to charge up, and then when the current starts decreasing, the capacitor will start discharging across the by passing current through the resistor. So this will discharge rather slowly with a time constant RC. So basically the output will look like this. So we will have this with the capacitor and the resistor in place. So for obvious reasons, this is called the halfway rectifier, because half of the wave is cut, and we have charging and discharging of the capacitor, causing a signal basically that looks like DC, but it has this ripple on it. So after rectification process, there will still be a 60 Hertz ripple that needs to be filtered on this rectifier. Okay, so how can we filter this ripple? So the filter circuits, we can have an RC high-pass filter. In this case, the AC source is connected to a capacitor and then to a resistor, and we're looking at the output voltage appearing across the resistor. Now, since the capacitive reactance of the capacitor is 1 over omega c, when omega is equal to 0 at DC, we will have infinite resistance. So this is not going to allow low frequencies to pass, but at high frequencies this is going to be 0, so it will act like a short, and delta V in will appear on the resistor totally. So at high frequencies we will have delta V out over delta V in approaching 1. At low frequencies it's approaching 0. So that's the characteristic of a high pass filter. If we look at the voltage across the capacitor, and so the AC source is connected to the resistor and the output voltage appears across the capacitor, they're still connected in series. Now this time at low frequencies, the capacitor acts like an open, so this is going to appear the voltage in that is the input voltage of the AC source will appear directly as the output voltage. So at low frequencies this will be approaching 1, at high frequencies this will approach 0, so this will be becoming a short, and delta V out will approach 0. So we have the opposite characteristic. And since the low frequencies are passed to the output, we have a low pass filter. Okay, so we can use these filter circuits, for example, to get rid of effects like ripples. Now we have an important theorem, maximum power transfer theorem, and here is the question. You have an AC source connect with a resistor R1, and you're connecting this to a load with resistance R load. What is the value of R load for maximum power to be delivered to the load? The current that flows in the circuit will be delta V divided by the total resistance R1 plus R load. So the voltage appearing on the load, delta VL, will be due to the sharing of the potential of two resistors in series. It will be R load divided by R load plus R1 times delta V. So it's proportional to R load. And the power that appears on the load is the current times the voltage, because we have purely resistive load. The current is basically delta V divided by R1 plus R load, that's the total resistance, multiplied by delta V load, which is R load divided by R load plus R1 times delta V, the input voltage. So you can see that this is delta V square R load over R1 plus R load square. So that's the power. Now we want to maximize the power appearing on the load resistance by taking the derivative with respect to the load resistance of the power and setting it equal to 0, we can find the extremum value. So the derivative of the top, R load delta V square, is delta V square. Derivative of the top multiplied by the bottom, R1 plus R load square, minus derivative of the bottom, 2R1 plus R load multiplied with the top, R load delta V, divided by the bottom squared, R1 plus R load to the fourth power, equals 0. We will see that delta V squares will cancel. One of the R1 plus R loads will cancel. So we have R1 plus R load minus 2R load equals to 0, as you can see here. So this gives us R load equals R1. So the maximum power transfer will occur when the resistance of the load matches the resistance of R1. And for if we generalize this to impedance, for Z load, what should we choose in order to have maximum power transfer? Z load should be equal to Z1 complex conjugate. So that's called impedance matching. All right, so what is complex conjugate? So if it is x plus iy, the complex conjugate is x minus iy, right? So that's the way we can conjugate complex numbers. So this is going to be the result for maximum power transfer when we use impedance instead of resistance. All right. So going back to our transformer, so our AC source has an equivalent, has a resistance R1, and it's connected to a transformer. The voltage that appears in the primary coil of the transformer, delta V1, is transferred to the secondary as delta V2 due to different number of turns in the coils, and this appears on the load resistance. For maximum power transfer from the AC source to this load, we must have an equivalent resistance appearing on the primary equal to R1. So remember that delta V2 is equal to minus N2 d phi b dt, and delta V1 is minus N1 d phi b dt. So in the iron core, we have the same flux. So delta V1 over delta V2 is equal to N1 over N2. And the power P1 appearing on the primary should be equal to the power P2 appearing on the secondary for an ideal transformer. So we have I1 delta V1 equals I2 delta V2. So I1 over I2 is delta V2 over delta V1, which is N2 over N1. And this power that we're going to see on the primary will be equal to I1 square R equivalent, which should be equal to I2 square R load. So we have I1 square over I2 square, input power equals output power, is equal to R load over R equivalent, and I1 square over I2 square is N2 over N1 square. So equivalent resistance that we see on the primary side is N1 over N2 squared times R load. And for maximum power transfer, this should be adjusted such that this equivalent resistance is equal to R1 for exactly the maximum power transfer theorem result to be met. So we can choose N1 and N2 such that this load resistance is transferred to the primary as an equivalent resistance, which matches the output resistance of our AC source. Impedance matching is achieved and maximum power transfer to the load is achieved. So you can see the logic behind using this transformer for impedance matching purposes. Now, before we conclude this discussion, I want to show you how we can formally do the analysis of the RC high-pass filter as an example. So in the complex impedance method, remember that we can replace these resistance and capacitance with complex impedances. Resistance is R, the capacitance is replaced with a complex impedance 1 over j omega c, where j was equal to square root minus 1, in order not to confuse with current. So now we have the sharing of the voltage between the capacitor and the resistor. So delta V out will be equal to R times delta V in divided by R plus 1 over j omega c. So delta V out over delta V in will be R j omega c divided by 1 plus R j omega c. So this is R j omega c plus 1. J omega c goes upstairs. R j omega c. So when we take the magnitude of this, we see that we have R omega c e to the j pi over 2 divided by this complex number square root of 1 plus R square omega square c square e to the j tangent inverse R omega c over 1. So the magnitude is R omega c divided by square root 1 plus R square omega square c square. So we have the transfer function from the input to the output given by this expression. When omega is equal to 0, you can see that the output will be 0. When omega is infinite, this one will be neglected and we will have R omega c over square root R square omega square c square, which is approaching R omega c over R omega c, that is 1. So high frequencies will be passed, low frequencies will be blocked with this functional behavior. We could obtain the same result using the Phasor method. The voltage phasor across the capacitor plus the voltage phasor across the resistor should be equal to the input AC source voltage phasor. So for the resistor, we have maximum voltage appearing I max times R, for the capacitor I max times XC. And in a capacitor, the current leads the voltage by an angle pi over 2. So when we plot the phasors here, we can put the current phasor I max times current phasor is here, I max times R. The voltage phasor for the resistor is pointing to the right with a 0 angle with the x-axis. So that's our reference. If we plot this one like this, then the capacitor will have a voltage phasor that is 90 degrees behind the voltage phasor of the resistor, because the the current that flows in the capacitor and the resistor will be the same. So this voltage phasor will be I max times XC. If we add these two phasors, we should get the voltage phasor for the AC source, delta V in max, which is I max times Z. So 1 over omega C, R and Z form this phasor diagram, and we can see that Z is square root of R square plus 1 over omega square C square. And the current is delta V in divided by the impedance. So delta V in divided by square root of 1 plus R square omega square C square divided by omega C goes upstairs. So delta V out will be the current multiplied by resistance. So it will be R times omega C divided by square root 1 plus R omega C parenthesis squared delta V in. So we obtain the same transfer function. Delta V out over delta V in is R omega C divided by square root 1 plus R omega C parentheses squared. And the relationship between the phase of the voltage and the current can be read here, right? So this tangent phi will be equal to 1 over omega c divided by r, and that will give us the angle phi between the current and the voltage of the circuit, the AC source voltage and the current that flows in the circuit. Okay, now we have seen the AC-DC rectification process. One way is to use this halfway rectifier, where we have a diode connected in series with a resistor and the resistor parallel with a capacitor. So when the diode allows the currents to flow, in the positive cycle, the capacitor starts charging, and in the negative cycle, the capacitor will start discharging across the resistor, and then it will start charging again and discharging, etc. And this will form a more DC-like signal with a ripple on it. And to get rid of the ripple, one can use a filter. And how do we filter out certain frequency components in a signal? We can use an RC high-pass filter or RC low-pass filter, for instance. And you can see that in an RC high-pass filter, because of the capacitive reactance of the capacitor, 1 over omega c, giving us a very high resistance at low frequencies, DC, and a very low resistance at high frequencies, or AC, we have a transfer characteristic as delta V out is equal to delta V in at very high frequencies. This is replaced by a short. At very low frequencies, this is replaced by an open, so we don't get any signal on the resistor. For a low-pass filter, we put the capacitor terminals is where we get the output voltage, and the resistor is connected in series with the capacitor. Now the capacitor will act like an open at very low frequencies, which means there won't be current flowing here. Delta V in will appear at delta V out. At very high frequencies, this will be replaced by a short, and it will appear as zero output voltage. We have seen the maximum power transfer theorem. When we maximize the power transferred to a load from an AC source with resistance R1, we see that the maximum power transfer will occur when our load is equal to R1. And we can generalize this to Z load and Z1. When the output impedance matches the complex conjugate of the impedance of the source, we will have maximum power transfer. And the transformer is one device that can be used to adjust the equivalent resistance that appears on the primary. The equivalent resistance is controlled by the ratio of the number of windings in the secondary coil and the primary coil. And by adjusting these numbers, we can get R load appear as R equivalent, which is equal to R1 on the source side for maximum power transfer. And finally, we have looked at the RC high-pass filter analysis. This can be done using the complex impedance method, as we did when we analyzed the RLC circuit. For this case, we replace the resistance R with complex impedance R and capacitance C with complex impedance 1 over j omega C, where j is square root minus 1. And using the parallel, the series connection of two impedances, complex impedances, the output voltage will be R times delta V in divided by the total complex impedance, R plus 1 over j omega C. And when we look at the magnitude of this ratio, we see that it is the transfer function R omega C over square root 1 plus R square omega C square C square. The same result is obtained using the phasors, where we add the voltage phasor in the capacitor and the voltage phasor in the resistor to the voltage phasor of the AC source. being careful with the phase relationships, if we have the same current flowing on these elements, so the current phasors are common. For the voltage phasors, we have to multiply the maximum current with R for delta VR and maximum current with XC for delta VC maximum value. And in a capacitor, the current leads voltage by pi over 2, or voltage lags current by pi over 2. We have the voltage phasor basically making a pi over 2 angle with respect to the current phasor. The current phasor is basically positive pi over 2 with respect to the x-axis as compared to the voltage phasor of the capacitor. So we have this pi over 2 angle between the two. And when we add these two phasors, we get the AC source phasor, voltage phasor, Imax times C. They all have Imax in them, so why not just replace them with the impedances, 1 over omega C R and Z. So this gives us the Z, the impedance of the circuit. And once you know the impedance of the circuit, delta V in over Z is the current that flows in the circuit, and the current multiplied by resistance is the output voltage due to Ohm's law. So delta V out over delta V in, we obtain the same result, exactly the same result as we did using the complex impedance method. So actually the complex impedance method seems to be a little bit easier because you don't have to remember these phase relationships between current and voltage for each circuit element. Instead, you have to know the complex impedances. For resistor, it's R. For capacitor, it's 1 over j omega C. For inductor, it's j omega L. So we can work with that. And finally, take the magnitude of the transfer, the ratio of output and input to get the transfer function.